Hi there, and welcome to L'Hopital's rule with Ava. So today we're going to go over L'Hopital's rule and how you use it. So L'Hopital's rule is really important. We use it when we are trying to find what a limit approaches, if it approaches zero or infinity or a definite number. L'Hopital's rule is really important because when we are given a limit that has an indeterminate form, and I'm going to write over here the indeterminate forms that you may see. So when we see one of these, we need to figure out a way that we can evaluate this limit despite the form that we are given. So for example, if you see 0 times infinity, you may wonder, is it 0 or is it infinity? You don't actually know what the limit is approaching because 0 times infinity, we don't know if it's 0 or infinity. And additionally, it could even be a finite number, so we use L'Hopital's rule to determine that number. Another important thing to remember about L'Hopital's rule is it only is used in fraction form. So all of these forms here that I've highlighted under blue, those are all forms that aren't in fraction. So we must have a way to convert those into fraction form, and we will go over that later in examples. We also need to know when we stop using L'Hopital's rule. When do we stop using that operation and actually evaluate the limit? How do you know if the limit is actually going to be infinity or 0? So we have to just keep reevaluating to see if it is in indeterminate form. And it has to be in its fraction form. So there's no more indeterminate forms that you see above in the blue. When we see those, that is the limit. But when we see it in fraction form, that is when we know we have to keep going. That can be a little bit confusing and totally understandable. We're going to go over some examples, what'll make it more clear, and I will be showing you when you actually stop evaluating and using L'Hopital's rule and when you actually evaluate the limit. But as for now, just remember that when you see it in indeterminate form in fraction, that is when you keep reevaluating using L'Hopital's rule. So now we're just going to go over how you actually evaluate it. So evaluating using L'Hopital's rule, all that means is that you take the derivative of the top and the bottom, but make sure you're doing it independently. You're not using quotient rule when you're taking the derivative. You're literally just treating the top as one piece and the bottom as one piece. Okay, now let's get into some fun examples. So we're going to start off with a pretty simple example just so we can solidify all the learning we previously did. We're going to look at the limit as x approaches infinity of 1 over x times 3x. Now, you may be able to evaluate this right away, and I don't want you to do that because what we're doing is we're using this example to solidify what we just learned and prove to you that in indeterminate form, it is not equal to what you see from that indeterminate form. So here's a really simple example. You have 3x over x. Now you can simply just evaluate this and eliminate the two x's and see that the limit approaches 3. But that's not what we're going to do. We are going to evaluate it using L'Hopital's rule. So using L'Hopital's rule, we have to convert to fraction form first, right? But that's just 3x over x. Now, if we're looking at the individual pieces, 1 over infinity is basically 0, and 3 times infinity is infinity. And when you are looking at those two multiplied together, we get 0 times infinity, which is one of the indeterminate forms that we mentioned earlier. This means that we need to use L'Hopital's rule. You already know this. I'm just writing it out so you can see visually how this actually works. And even though we get 0 times infinity, there still can be a numerical answer. I'm just going to quickly evaluate this as you normally would a limit just to prove to you that it equals 3 and that just because we're getting 0 times infinity does not mean that the result is going to be 0. That's what I wrote here as a little bit of a side note in yellow. Okay, we're going to head into a second example, which is a little bit more complicated and requires more work. So here we have the limit as x approaches 0 of tan x minus x over x cubed. Now let's evaluate all these pieces individually to see what we get as an indeterminate form. So tan x as x approaches 0, Well, x is just 0, and then x cubed is 0 cubed. So when we look at all of those individual pieces, we get 0 minus 0 over 0, which is just 0 over 0. So here we have indeterminate form. This means that we need to use L'Hopital's rule. Now, in all of my examples, you're going to see that I write a little h right above the equal sign in pink to identify that on this step, I'm using L'Hopital's rule. So here what I did is I took tan x minus x, put it in a bracket, and added a prime on the outside. That is my notation of saying that I am taking the derivative of tan x minus x. I did the same thing with the x cubed. Now we're going to actually take the derivative. So the top is simple. We just take the derivative of tan x, which is secant squared x, and the derivative of x is just 1, so we end up with secant squared x minus 1 on the top, and on the bottom we have power rule, so we just get 3x squared. Now once again, we're going to reevaluate. At every single step, you're going to reevaluate. Every time that you take a derivative, you are going to reevaluate. So here we're looking at secant squared x. Secant 0 is equal to 1. So that means at the top we get 0. And at the bottom we also get 0. This means that we are in indeterminate form once again, which means we have to use L'Hopital's rule. Now, if we got 0 and a number on the bottom, we would be able to evaluate the limit as being 0. But since we're getting a 0 on the bottom as well, then we have to use indeterminate form. We have to use L'Hopital's rule. So what I'm doing here is using a trigonometry identity. I really can't say the word trigonometry. Don't know why. But secant squared x minus 1 is just tan squared x. You could evaluate secant squared x minus 1 on your own if you want to take the derivative of that, but tan squared x is easier. So that's what I'm writing down, just simplifying it a little bit. And here you can see I've written the pink h again, which means that in that step I took the derivative. So I didn't do that prime thing or in the brackets that I did earlier, because here I'm just jumping to writing out the derivative since I believe you already got the concept down. And so here I just took the derivative. You can reevaluate that to see if I was correct, or just practice your derivatives in general. Once again, I'm reevaluating. So I didn't reevaluate at the tan squared x step because that one I didn't change anything. I didn't take any derivatives. So in this step, since I took a derivative, I have to reevaluate. A lot about math, especially when you get to higher levels, is about simplifications and looking at your problem and noticing what you can do in order to solve this and solve it easier and more efficiently. So that's what I'm doing here with the colors. I'm showing you that this problem can be separated. You can take this 2 secant squared x and put it over 6. And you can do that because you know that secant squared or secant of 0 is actually 1. So that all that's highlighted in orange is something that is going to give you a finite number. And taking that out makes operations a lot easier because now you don't have to deal with that anymore, and you don't have to create or you don't have to use that in your derivatives because now you can just simply evaluate it. The skill of being able to actually look at something and see, okay, this is how I can separate things and evaluate it is so hard, but so important. So when you see it happen, you're like, oh my God, that makes so much sense. But then when you actually go to do it yourself, it is so much harder to see. So I urge you to practice looking at really interesting simplifications. I remember when I first approached this problem, I did not see that simplification because it's a hard one to notice. The key thing to noticing this one, and that's what I try to look for in simplifications, is how to notice them as a general rule, not just how to notice it with secant x, how to notice it as a general rule. So for this one, noticing it with a general rule would be understanding what you can do when a trigonometric, I can't say the word, but you get what I'm saying. When that actually evaluates to a number. And earlier we evaluated secant 0 equaling 1. So that means that you know that that has a number. And you have a 6 also at the bottom, right? So you could pull that out since we have multiplication, and now you know that you can actually evaluate something finitely. And whenever you can pull out a constant, That is, you should always do that in every single problem. Well, obviously I can't say always, but as often as you can, use your critical thinking. Nothing is ever definite, so you can't say always do this, but it almost always, I'll say almost always helps. I'm getting a little bit carried away with my pieces of advice, but I just want to let you guys know that you're not alone in struggling with this. And if you lock down these core concepts, you're able to do a lot of other math problems, especially as you go into higher level. Like taking university math for me was really difficult because I wasn't used to having to identify these kinds of things. No one warned me about that because high school level math was a lot more simpler. So if you can lock this down, and realize how to find these simplifications in high school, in university, you will be sailing through. Anyways, enough about my life lessons. Let's keep going about the problem. So, what I did here is I pulled it out, which you already know, and then I just evaluated it. We know that secant x is 1, so we just get 2 over 6, which can just simplify to 1 over 3. And then once again, we have tan x over x. Now we see that that is 0 over 0 once again, which means we need to use L'Hopital's rule. The good thing is the whole secant thing is out of the way. We have 1 over 3 that we've just pulled out as a constant, and we don't have to L'Hopital that because it's just a constant. So now we can just look at the tan x, and the derivative of tan x is secant squared x, and derivative of x is just 1, which is great. Now we get a 1 on the bottom, and we know that secant squared x actually just approaches 1 when you get to 0. So we just have 1 over 1. And that means that our answer to this question is 1 over 3. Now here on the side, you might have seen me draw little dots. I was just showing that I was continuing writing the limit. I don't really write them. In high school, I got docked a lot of marks if I didn't keep proper form. University, all multiple choice, so no one cares. But don't forget to write your limit if your teacher specifically needs you to do that, especially in high school. I'm just scrolling back up here because I'm just going to reiterate that this step with the orange and purple is the hardest step of this problem. Without identifying that, this problem would be a lot more complicated and you would have to be taking derivatives that would just take way too long. Um, and it's totally fine if you wouldn't have gotten that at first. It's just practice, practice, practice. And one day you will get it and you'll be able to identify it, especially when you're looking for it. With that said, we're going to head into our last example. This example is quite challenging. It isn't something that is really figured out intuitively unless you're taught it. So you have to bear with me with this question, and you may struggle a lot, but I'm going to try my best to explain it as best I can. Alright, so here we are looking at the limit as x approaches 0 from the right of 1 plus sine 4x, all to the exponent of cotangent x. Okay, so first when we're looking at it, let's evaluate the individual pieces to see if we have indeterminate form. So sine 4x, we're looking at as x approaches 0. So sine of 0 is 0, so we get 1 plus 0, which is just 1. And then cotangent 0 approaches infinity. If you have a problem with these limits, like these simple limits, I encourage you really to look at Desmos and just put them in the graph because visualizing it way easier to just remember the what these simple trigonomic functions approach. Now with that said, we get 1 in the bracket and then infinity on as the exponent. So that means that we have 1 to the power of infinity. Now that is a indeterminate form. If you forget the indeterminate forms, refer back to the list, or you could search one up on Google, which has probably a lot more aesthetic options than my stupid list, but feel free to keep referring back to that until you are really comfortable. Now, I'm going to break this up into step by steps because I really want to make sure that this is locked into your brains. So, the first step is we have an exponent here, right? And we need to turn this into a fraction. So, what we're going to do is get rid of the exponent. Now, what is something we know that gets rid of exponents, right? We have logarithmic properties. That is what gets rid of exponents. So we're going to use ln. I use ln all the time in university. I don't think we touched log even once. So we're always using ln. What we do here is we do a substitution. So you can use any letter to do the substitution. I'm just using y. I don't know why, but Yeah, so I'm going to use y, and I'm going to let y equal that whole entire thing. So the whole entire equation that is inside the limit is going to be my y. And this is because, wow, I don't like the fact that I used a y because I'm just going to keep saying y. But anyways, so I used that as the substitution because when you take the ln of anything, you take the exponent and you put it on the outside. So that's going to allow us to bring the exponent outside of the, or bring the exponent to the left side of the equation, and we're not going to have an exponent anymore. So when you're taking ln, you have to take ln of what's on the inside, and then that's when you can remove the exponent. So here I wrote cotangent x multiplied by ln of 1 plus sine 4x. Now that we have that, we can convert it into fraction. Now what I'm doing here is also showing you that it is still an indeterminate form. 1 plus sine 4x is just 1. Ln 1 is 0, so we have infinity times 0. So it's still an indeterminate form. We didn't avoid that form by doing a substitution. Now, our step 2 is going to be converting it into fraction. Well, that was our whole entire step, but we had to do a little bit of a side step, which was substitution. So to convert it into fraction, we just see multiplication, right? And what we do with multiplication is we can actually take the reciprocal of something and put it on the denominator, because that is the same as multiplication. So here I took the cotangent x, and I said, okay, let's do 1 over cotangent x, because that's the same as multiplying by cotangent x. Now, you could have done 1 over ln and everything else. That's just longer to write, and it's more complicated to see. So cotangent x, more simple. We're just putting that right down on the bottom. So now that we've done that, you can reevaluate and see if it's still in an indeterminate form. I promise you it is. Key thing to remember is what we're doing here is we are taking the limit as x approaches 0 of ln y. We're not taking it of what we did originally. So if you are in high school, you must write this down. You must make sure that you're consistent because it can get really confusing, and teachers can definitely dock marks for that. So just make sure that you are clearly writing that down because it is a limit of ln y, which we're taking right now because of that substitution. Anyways, let's get back to the problem. So right now we are going to take the derivative. Over here I wrote the derivative quickly. You can review that if you want and go over how to do that. But anyways, I'm reevaluating it. So cos of x, or cos of 0, is just 1. And then 1 over 1 plus sine x is just 0. So we just get 1 over 1. So that ends up simplifying at the top. We get 4 times 1. And then at the bottom we have secant x. So secant of 0 is just 1. So then we get the answer of 4. Now, whoa, you're finished. That was easy. It was not easy because everyone forgets what they have to do in the next step. Even though you've gotten an answer, that is the answer you have gotten for ln y. That is not the answer of the original question. So, especially on multiple choice tests, they're going to trick you. They're going to put 4 as the answer, and you might fall into that trap. So, this is your warning. Do not fall into that trap. So what I'm doing here on the right is I am showing you that this is the limit as x approaches 0 of ln y, and that is equal to 4. Now we have an expression. Now we can take this expression and we can actually solve for the limit of y using isolation. So we know that we can take anything to the power of e. Now if you used log for this, you would be taking things to the power of 10. Now, using exponent rules, we're going to do e to the ln y and then e to the 4. E to the ln y just simplifies to y, and then e to the 4 just remains e to the 4. This means that the limit as x approaches 0 of y is equal to e to the 4. Here I am just doing the dots again, showing you that I'm supposed to be writing the limit all the time. I just always forget. Therefore, we can get our answer where the limit as x approaches 0 of the entire expression from above, which was 1 plus sine 4x to the power of cotangent x, is equal to e to the 4. You have finished your question. Good job, and I hope you have an amazing day.